Hello, welcome to the course on microwave and antennas. In this lecture, we will learn about how to visualize a transmission line. To derive the transmission line equation and understand the mathematics, let us start with the telegrapher's equation. It was originally developed for low frequency telegraph communication, and it is well applicable to radio frequency or microwave frequency systems. Consider a section of wire or a transmission line. As we discussed before, the wire can be very long compared to wavelength of operation, so we are considering a small section or portion of a wire. It looks like this. Remember, the entire wire length can be basically made up of these small sections. These are the current and voltage functions. And these functions look a bit complex, so let me explain a few terms here. I stands for current, V stands for voltage, T stands for time instant, Z stands for the distance along the length of the line. Since we are considering a small section of line, delta Z represents the small section of a long line. If we were doing DC or low frequency circuit analysis, since wavelength is very long, Iz of t would be equal to Iz of I of z plus delta z comma t. Similarly, Vz of t would be equal to V of z plus delta z comma t. Since current and voltage are same across the length of the line except for some fixed resistance. So we would have just written I of t and V of t without reference to any position z on the line. But here, in case of high frequency circuits, the current and voltage changes based on the position of the line where measurement is made. Thus, we can say that in this case, Vz of t is not equal to V of z plus delta z comma t. Similarly, the current equation. So why is that so? That is because at high frequencies the wire is never a simple resistance, but it has other elements which are inductance, capacitance, and conductance in addition to the resistance which is seen in the DC circuits. So at a microwave frequencies the wire looks as shown in this image, while at the DC frequency or the low frequency it has only a resistance. You may have a question why I have shown two lines to represent a wire. This is one line, this is the other line, instead of a single line. That is because every transmission line has one wire for sending the signals and the other wire is considered as the return path, or also sometimes used as ground or the reference path. All measurements are with reference to the bottom line. So let me define the new variables that you see here. R delta Z is the resistance over the small section of wire delta Z. Similarly, L delta Z is the inductance over the section of length delta Z. Similarly, C delta Z is the capacitance over the length delta Z. G delta Z is the conductance over the section length delta Z.